Okay, so the new section, 3.1, functions and function family notes. Analyze relation to functions, recognize different functions and apparent graphs. Well, a relation is a mapping of input values and output values. The input is called the domain, the x values, the output is called the range, y values. A relation is a function if and if there's only one output for each input. We'll talk about that. That's the most confusing part. So, I'll make a little chart here to reference throughout. X and y. Okay? Nice thing is x comes before y in the output. Well, so does domain and range. So does input and output. And so does H and V for horizontal and vertical. It just all plays out very nicely. So if you notice here, it says the input is the domain is the x values. The input is the domain is the x values, which just happens to be the left and right of the graph. And the output is the range, which is the y values. The output's the range, which is the y values, which is our up and down on the graph. It's going to come in very handy when we're dealing with any of this. Okay, say the domain range of each relation. Is the relation a function? So what we're going to do is we're going to look at the input, or again, the x and the y, or the domain and the range. Okay? And we're going to look at these and list them here. So we're just going to put braces here, and we're going to list the domain, the x values. -3, 2, and +3. For the range, we're going to list the output, or the y values. -2, 1, and 3. Now, the whole idea of a function is kind of the confusing part. So let's think about this. If I took my calculator, and I want you to write this down because this is going to be the image you're going to remember that's going to help you keep this in line, because it is very confusing. Okay? If we type 3 + 7 into the calculator and hit equals, we can get 10. If we clear it out, type 3 + 7 equals, we get 10. And if we did it a third time, and a fourth time, and a fifth time, hopefully every time we did it, we would get 10. Now, if we took our calculator out and typed in 3 + 7 equals and got 5, and we typed it, hit clear, and only I fat fingered it, 3 + 7, I got 18. And I did it again, I got 3 + 7 equals -38. Well, at that point, you would say your calculator is broken or not functioning. Your calculator is not functioning. If you put in 3 + 7, you only expect out one answer, 10 every time. So inputs can only have one output. You put something in, you can only get one number out. Otherwise, your calculator is not functioning. But let's think about 10. We can get 10 a lot of different ways. 9 + 1, 100 divided by 10, 40 - 30. These are all different inputs that would give us the output of 10. So, using that analogy of the calculator, when we put -3 in, we get 3. We put 2 in, we get -2. We put 3 in, we get 1. Every number in only has one number out, so that is, yes, it is a function. Go over here to number 2. Input is our D, so it's 4, 8, -3, and 5. Our range, or our output, is 12, 5, and 6. We put 4 in, we get 12. Cool. We put 8 in, we get 5. Cool. If we put -3 in, we might get 5, we might get 6. At that point, we know it's not a function. Because when we put the one input of 3 in, -3 in, we don't know what we're going to get. 5 or 6. So that's not a function. Number 3. Now they're listed in traditional XY formation. So you just find all the x's. -2, 5, and 0. All the range is all the y values. 1, 4, and 3. Well, -2 has one number, 5 has one number, 0 has one number. So yes, it is a function. Now, number 4. Domain is 5, 4, and -2. The range, the y values, is 2 and just 7. I know there's more than one 7, but we don't have to write it for every occurrence. It's just 7. So, 5 gives us 2, 4 gives us 7, and -2 also gives us 7. So we have to think back to the calculator analogy. Is that okay? Is it okay to have more than one way to get the same output? And yes, that's okay. 4 gives us 7, -2 gives us 7. That's all right. We have a yes. Number 5, we have XY chart now, or an X, half of X chart. So the domain is the X values, 2, -1, 3. Already wrote 2, so we don't have to write it again. -3. The Y values, or the range, is 5, 0, -5, 4, and 7. Well, 2 gives us 5, but 2 also gives us 4. At that point, it's no. It can't be a function because when we put in 2, we don't know what's coming out. And we don't want that uncertainty. Okay. The vertical line test. And the vertical line goes up and down like a column. Okay. So the vertical line test works like this. You drop a vertical line through your function. If you hit only one time, only once, then you have a function. But if I drop through and hit more than once, then no, it's not a function. It failed the vertical line test. Okay? Now, someone always will say, well, hey, if I put one right here, it only hits once, so it passes. You have to be able to do the vertical line test multiple times. This one right here does not prove it or disprove it. You got to be able to do it multiple times. And obviously, it is going to hit more than once. So that's not a function. Okay, now, back in algebra, you had y equals all the time. Y equals x plus 1, y equals 3/2 x minus 7, y equals 4. Okay? And that's fine and dandy, but now we got to be able to do more stuff with it. We have to be able to do more things with it. And in this case, we have what's called function notation. And this means we read it like this: f of x. That's how we read it. Or g of x, or t of x, or s of x, or r of x, whatever. It can be pretty much any letter in the alphabet. Now, why do we do that? Well, let's say I have a side hobby of making toy trains. And I'm just doing it and I give it to presents. And somebody says, hey, you should sell those. Those kids really like them. Okay, so I start making and selling them. I just have my basic train. But it becomes more and more of a business. And now people want other color trains. So I assemble a manufacturer. And I have a red line, a blue line, and a green line. Well, businesses use this all the time, function notation. They need to be able to distinguish between different parts of their company or different products. If you said everything was y equals, you wouldn't be able to have different functions happening on different ones because they have different costs sometimes. Some paint might be more expensive than another, whatnot. So I would call my green line g of x, my blue line b of x, my red line r of x. And that would allow me to have different functions going on at different times, but then be able to distinguish which one I'm talking about. So over here, I have f of -6. That means I'm going to find the f function and put -6 right there. So I do that. I write f of x. Now some people will write f of negative 6, and that's perfectly all right. The problem with it is some people then when they get through the problem are like, what do I do with this negative 6? In that case, I would say just write f of x. Because remember, it's the same thing as y. Equals 2 times negative 6 squared minus 8. So, negative 6 squared times itself is positive 36. 36 times 2, 72. 72 minus 8 is 64. Which means, if I put in input negative 6, I get output of 64. If I put the number 10 in, I'd have 200 minus 8, 192. If I put 0 in, 0 squared is 0, times 2 is 0, minus 8. My input 0, my output is negative 8. Every XY table you've ever done is an input-output table. You put in for X, you solve for Y. 3a, do the same thing. F of X equals 2 times 3a squared minus 8. Now here you gotta be careful. It's not 3a squared, it's 3a in parentheses being squared, which means the 2 goes to the 3 and the a. So in other words, you're going to do 3 squared, which is 9, and a squared, which is a squared. But we can't forget this little 2 out here. Kind of like when we were dealing with radicals. You can't forget that this means 2 times 3a squared. So 3a squared is 9a squared, times 2 is 18a squared, minus 8. Now some of you might be tempted to write right now 10a squared. You can't do that. You cannot put together letters and numbers. That is it. This is the answer. You cannot go any smaller, any more compact. You can't shove them together. Okay, h of negative 3. Now this time we're going to plug this one up into this function right here. So we're going to do h of x equals 2 times negative 3. Oh, I'm on the wrong one. I said it, I still didn't do it. So it's still negative 2, that's what threw me off, times just negative 3, no squared, and then plus 6. So negative 2 times negative 3 is positive 6. 6 and 6 is 12. So I input negative 3, output is 12. Okay. Linear equations. Oh, that stayed. I meant to erase. I don't know why that didn't erase. Oh, I know I didn't erase because I drew it with this. Okay, it's a line. Linear equations are lines. It's in the word itself. So I'm just going to pick some numbers for negative 2, negative 1, 0, 1, 2. Well, remember, this is basically y equals x. In other words, this column is the same as that column. Negative 2, negative 1. So, if I graph this, negative 2 is right here, negative 1, 0, 0, 1, 1, 2, 2, and it just keeps going. 3, 3, 8, 8, 10, 10, negative 10, negative 10. Every number on x matches every number on y. So it's a diagonal line through the quadrants. Perfect diagonal. Now, here's the thing, it's going to be very important. This is a very important chapter of the entire semester. This is a lot of stuff here is going to be coming back and not going away anytime soon. So, domain. Remember, we talked about the fact that domain is the x value. We also talked about that it is horizontal. The x-axis is horizontal. So when we're talking about the domain, we're not just listing the x and y values anymore. We're trying to find out forever and ever what's the domain. So we ask ourselves, how far to the left is this going to go? How far to the right? And for the range, how low and how high? And you're going to ask yourself that question every time you're doing this and get into that habit. So the domain, When I say how far left, well, it's going to keep going that way, to the left and down. So it's going to go towards negative infinity. And it's not going to stop. It's going to keep going left, 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 left. And it's also going to keep going right, 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 towards positive infinity. And the range is going to do the same thing. It's going to keep going down and keep going up. So from negative infinity to positive infinity. Absolute value. I'm going to use the same numbers. Negative 2, negative 1, 0, 1, 2. Well, the absolute value of negative 2 means how far away from 0 is negative 2. There's 2 spaces. And 1 and 0 and 1 and 2. Okay? So when we put this on here, we get a V for absolute value. V for absolute value. And it's always going to be this shape. It could be going down. This is positive, that's negative. You could have an upside down absolute value if you put a negative sign right out here. I'm not doing that here, but that's what they can look like. You can have one going down also. Because if you had an absolute value with negative out here, all these would be the negative. That would be going down. Now, how far left? Same thing, negative infinity. How far right? Same thing. Here's the tricky part. The range. How low does it go? Well, it goes all the way down to 0. It's not going towards negative infinity. It kind of comes down, hits the wall, and bounces back off that way. And it's the way up to positive infinity. But here's the tricky part. It's actually touching at 0, 0. It's hitting right here. We have a point right here at the origin, 0, 0. Which means we need to use a bracket because it includes that number. It's actually touching at 0, 0. So we use a bracket. Okay, quadratic. A quadratic is going to give you the shape of a parabola, which means it's going to look like this if it's happy, and this if it's sad. A smile or a frown. So instead of a V, we got kind of a U. Let me just say numbers. Negative 2, negative 1, 0, 1, 2. And I'm going to square that. So negative 2 squared is 4. Negative 1 is 1, 0, 1, and 4. So it's going to look similar. Negative 2 is going to go up to 4. Negative 1 is going to be here. 0, 0, 1, 1, and 2, 4. It's going to look very similar to our absolute value. The only thing is it has a slight curve to it. It's not straight lines. And the domain range can be very similar. It's going left and right the same way as our absolute value. And the range is also hitting at 0, right here. So since it's hitting, we need to use a bracket. And then it goes up and forever. Forever and ever, up to the sky. Okay, square root. Now for square root, I'm not going to use the same numbers. Okay, I'm not going to put any negatives in for x because you can't take the square root of a negative number. And to make life easy on myself, I'm only going to use perfect squares. I'm not going to use these boxes. Because the next number I would use would be 16, that's off our chart. And I would use 25, but it's off our chart. This will give us a good enough representation. Square root of 0 is 0, square root of 4 is 2, and square root of 9 is 3. That's enough to graph. It's enough to give us a visual representation of this shape. 4, 2, and 9, 3. And this is the graph of a square root function. Now, we ask those same questions. But, look at this. How far left does it go? So, it's a similar idea. How far left does it go? 0, right here. Okay? So it's going only to the left, so I use a bracket, because once again, it's hitting this point. How far right? positive infinity. How low does it go? Again, 0 on towards positive infinity. It's slowly creeping up. All right, more function families. Cubic. I'm going to put -2, -1, 0, 1, 2. These will work because you can get these numbers. So -2 times -2 times -2 is, remember, -8. Negatives in groups of odd numbers are always going to be negative. Negatives in groups of even numbers will be positive because every pair of negatives makes a positive. So -1 is going to become -1, 0 is 0, 1 is 1, and 2 is not 2. 2 is 8. So I'm going to put -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8. And I have a snake. Okay? Now, if you look at this and think back to our parabola, think back to the parabolic shape we had here. When we use these numbers, look at the shape of it. Okay? It's doing this, right? If you go to what we're doing right now, it's a very similar shape. This looks very similar right here. The only difference is this side is going this way. And it's going to happen for all odd numbers. Something to the 5th power is going to have this general shape, whereas something to the even power is going to have this general shape every time. Because the even allows us to get, even the odd allows us to get negative answers down here, going this way. Okay? That's why you're going to have that general shape. But at least see the relationship between the cube and the square. Now I'm going the other way. Cubic, root. I'm going to use these numbers right here. -8, -1, 0, 1, 8. Why? Because I've already got my answers right here. So the cube root of -8 is -2, -1, 0, 1, and 2. So -8, -2 is down here. -1, -1's here, 0, 0, 1, 1, and 8, 2. Whoopsie. Line up, 8, 2. Well, look what I got. I got my same snake just going left to right. Like it just fell over. Instead of going north to south, now it's going east to west. So let's do the domain and range. I forgot to do it on the last one, so they're kind of going to be the same. Domain is -infinity to positive infinity. It's going to keep going left and right. And my range is also going to be the same. That's going to be the same for both of these. Because they're continuing to go left and right. And they're continuing to go up and down on both of them. No difference. Okay, exponential growth. I'm going to use 2 to the power of another number. So I'm going to use -1, 0, 1, 2, 3. So remember back to what we just learned. 2 to the -1. Okay, you're babysitting the kids. You're technically upstairs. They're being bratty and noisy. You're going to send them downstairs to get a better attitude. So that gives you, instead of -2 over 1, 1 over 2, which is 1/2 or 0.5. Then you plug in 0. Anything to the 0 power is 1. 2 to the first power, anything to the first power is itself. And then we have 2 squared, and we have 2 cubed, which we already know. So now we're going to graph this. 3, 8, 2, 4, 1, 2, 0, 1, and then negative 1.5. And all I want you to do is I want you to draw it from the top down, because what's going to happen is it's going to just come here and get closer and closer to that line. It's actually hard to draw, but it is never going to touch that line. Now somebody in another class said, I don't understand it. That seems impossible. How can it never touch? Well, let's think about it. I can plug any number in right here as long as it's greater than 1. So if I plug in the number 1 million, I mean negative 1 million, okay? So negative 1 million, this side, I do 2 to the negative 1 million. You don't have to write this down. All that's going to mean is that's actually the number 1 over 2 to the 1 million. So it's going to be 2 times 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 2, all the way up to a million. Some huge, 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 huge number. Okay? But it's going to be 1 over that. So as this number on the bottom gets bigger and bigger and bigger, you're actually talking about a teenier, tinier, tinier, tinier number. I'm talking microscopic. You would not even be able to see. You couldn't draw this out even to negative 20. You couldn't draw it. You just end up touching the line or going like, you couldn't do it physically. A computer could do it, and if you magnified it, you'd be able to see space. And you magnify it again, you'd be able to see space. But you can keep going on forever to infinity, negative infinity, and there would always be a space. I know it's hard to understand, but it would not ever touch. So therefore, this one's a little bit different. The domain's the same. It's going to go left forever, and it's going to go right forever. But the range, how low does it go? Well, we just said it's never going to hit 0. So instead of using a bracket, we use a parentheses, which you already understand the concept of. It's not including the number 0. It includes 0.0000000000000 whatever, but it will never touch 0. Okay? Negative 3, negative 2, negative 1, 0, 1. Okay? Well, this is just the flip of this one. So this is going to be 8. This is going to be 4. This is going to be 2. Anything to the 0 power is 1. Anything to the first power is itself. So 1/2. Okay? And the reason it becomes positive is because remember this negative exponent is going to make it flip. So instead of being 1/8, 1/2 times 1/2 times 1/2, you flip it and make it 2 over 1, or 8 over 1, or whatnot. So the domain of this bad boy, we go to negative 3 and go up to 8. We go to negative 2, go to 4. And negative 1, go to 2. 0, 1, 1.5. It's going to be the same thing, never hitting 0, but going this way now. That's decay. So left and right forever. Range, 0 but not included, forever. Well, that's the announcement for the last problem. Okay, so on this last problem, we're looking at this graph, and we have the domain again, and we're going to look again ask the same question. How far left does it go? Well, right here, it's going to negative 6. And since it's a solid dot, that means we use a bracket. How far right is it going? It's going towards 8, and again with a bracket. Range, we ask ourselves, how low does it go? That's right here at negative 2, with a bracket because it's a solid dot. If it was an open dot, we use parentheses. And then how high does it go? 4. And since it is on this line at 4, we use a bracket. Is it a function? Well, we drop the vertical line test over and over. We only hit once, so the answer is yes.